topic for today. How do you actually select, like pick out a slice? Just excite the spins in a slice. And to understand this, so we'll just sort of go over what a gradient does, how that sort of geometrically looks in the brain. But we also require a frequency selective RF pulse. So you need a gradient plus a frequency selective RF pulse to pick out a slice, two things. And then to understand how that thing works, and we'll talk about the convolution theorem. So every well-educated college student should know about convolution. So convolution and the Fourier transform are very closely related. And so we'll talk about how they're related and how you can just use that to reason without really doing any math. Just kind of graphically reason about what some kind of setup is going to do. And so we'll try to figure out the frequency selective pulse from the point of view of looking at convolution and the Fourier transform. Now, sometimes, you think like, oh man, I had trouble enough with the Fourier transform. Now you're going to tell me that convolution is related to it somehow, and then that's going to somehow fix it. But hopefully at the end you'll see that it's kind of a simpler two-dimensional. It's always, sort of a little two-dimensional way of thinking about these abstract concepts. So start off with the gradient. So we've already said this many times, but what does the gradient do? So if you look at it from the top, if you look at an x gradient from the top, here's somebody in there. What it does is you've got this really big B0 field. And so if I just draw the vectors for the B0 field at each point along, just going across the head, this is what they look like. They're supposed to be all the same length. So they're really big because the B0 field is very big. And then when we turn on the gradient coil, that's the thing that makes noise in the MRI. And one of these days we'll go over to the MRI center, take a field trip over there and fire it up. So they're all the same length. And when you turn the gradient on, what happens is you add a little bit or subtract a little bit from the BZ field. So remember, this is the BZ direction. You add or subtract a little bit as you move in the x direction. So basically, if you turn the gradient on, you'll add a little bit on this end, and then you'll do nothing in the middle, and then subtract. I exaggerated how much you're adding and subtracting, but basically this is what you do. So you add a little bit on this end and subtract from the other end. Now, what happens in the other axes? So if you move up, up and down, it doesn't change. And if you move in the z direction, it doesn't change. So I just drew for one, slice slice going through the head right here. But if we went to the chin, the same thing would apply. It's not totally true. It's kind of close. But the idea is that you're trying to just affect the BZ field as you move in the x direction, but not affect it as you move in the y direction or the z direction. So that's an x gradient. So this is so what we illustrated there was an x gradient. So if you think about this, in 3D, so here's kind of like a little sort of cube of 3D. Which direction do I have the guy's? I got the guy's mouth this way. I drew the BZ backwards. So, well, some magnet manufacturers have the BZ in the opposite direction. So I kind of drew it backwards like that. normally the Z component would sort of come out toward your feet. But I drew it coming out toward the head, but it doesn't matter. You get the idea. So let's put a person in there. So here's the person in there. It's an ugly person in there. Sorry, guy. So what happens is you're basically, when you turn the gradient on, if you take a slice through the person, so here's a slice, that's the precession frequency of that slice is going to be, the expected precession frequency of that slice is going to be constant along this little plane here, this sagittal plane. So what I'm trying to draw here is a sagittal plane through the person. So that means like a thin plane sort of cutting down in this direction through their head. So if we just make a graph of the expected precession frequency as a function of x. So this is our x direction, and this is our y direction, and this is our z direction. So if we make a graph of what you expect the precession frequency to be, so if we plot it as a function of x. So we said that the gradient supposedly doesn't change anything in the y when you move in the y direction or the z direction, so x is the only relevant direction. And this, what I'm plotting on the y-axis is the bz. So that's the bz moving in the x direction, and we'll have a graph that's just a linear, gradient graph. And so if we take a little slice, say like somewhere in the x direction, like the one I drew there, that corresponds to a range of precession frequencies like that. And so for that, so the B0 field in that little range is going to cause a particular precession frequency. And what is that frequency? So that frequency equals this gyromagnetic ratio, and a lot of times there's always this 2 pi because you can either have an angle measured in radians, which is like a distance of 1 along the circumference, or you can have it measured in cycles, which is like all the way around. And so there's a 2 pi difference between those two. And so sometimes you see that symbol, and what that symbol means is the gyromagnetic ratio divided by 2 pi to sort of like allow you to have a frequency over here instead of radians. So frequency cycles per second, full cycles per second instead of just radians per second. So the frequency that you're going to expect to have the precession occur at in this little thing is going to base in the middle of it is going to be, whatever the B0 field is, plus whatever the gradient did. So here's the extra b that comes from whatever the x gradient did. So remember, you're only concerned about the z component of the b, and so we just added that on. That's just the very first equation that we had, which was that frequency equals gyromagnetic ratio times the z component, the b0. Except, we wrote it out in frequency. The original one was like, just this equals this times b0. So that's the same thing. So that's the frequency you expect to get in the middle of that slice. So So now the problem is, and you can sort of see how, like, as soon as we turn that gradient on, we immediately, if there's any precessing protons, we immediately cause them to precess at a different frequency, which is defined by this. But that's not enough just to turn the gradient on. We actually have to have a frequency selective RF pulse. So the idea is that if we feed in a small range of frequencies, so this would be like the small range of frequencies. So if basically we just want, a little frequency, width here. So we want a little range of frequencies. Then what we would do is we would only excite, protons that were at that part of the gradient field, which corresponds to a plane. So that corresponds to a plane. And now you might wonder, like, what if you don't want a plane there? What if you want a plane in a different axis? It turns out if you just turn another gradient on, you'll have the effect of tilting the plane. So you can basically pick out any old plane that you want. We just picked out a sagittal plane. So this is a sagittal plane, which just means like a plane down the midline, like that, or any direction, but in this direction, as opposed to, say, like in this direction, or there's three possible planes, perpendicular planes. So this is the sagittal plane. So now all we got to do is figure out, like, how do we make an RF pulse that actually has just a narrow band of frequencies in it. So that's the goal for the rest of the lecture. And so what we want. So we already know from the last time that if you have a narrow band of frequencies like that, so if this is the frequency, the frequency domain, that corresponds to. So if we take a Fourier transform to go from the time domain to the frequency domain, we already know that the inverse Fourier transform of this little rectangle function is this thing called a sinc function. And so this guy is called rect for rectangle, and this guy is called sinc for sine cardinal. And what does that equal? That just equals, it's a very simple equation, just equals, so sinc of t just equals sine of t divided by t. So if you just take the sine of whatever time you're at and divide it by t, you get this funny function. It kind of looks like a cosine. It looks like a damped cosine. So that's the Fourier transform. You could do an inverse Fourier transform to get from this rectangle to this, or forward Fourier transform to get from this to that rectangle. So, but that's around zero frequency. So this is zero frequency and zero time here. So we don't want that. What we want is, if that's zero frequency, we want a band of frequency that's off to the side like that. There'll be another one over here, but we'll ignore that one for the time being. And so what we want is a band of frequencies that has a particular frequency width. So that's the frequency width, and then a particular center frequency. So that's frequency center. So how do we get that? What does that correspond to? So there's several ways of approaching this that vary in complexity, but in accuracy, is actually measured by what if we do it and just see what happens. But before I go on, I'll just stop for a second. So questions about this? So the idea is we put on a gradient, and what that does is it makes a plane, all these different planes, and each plane will be resonating at a different frequency. And then all we have to figure out is how can we generate a narrow band of frequency so that we can just affect a plane. So one way of thinking about this is we could use the Fourier transform. And so what we want to know is what do we need to do to the B1 field as a function of time? So that's what we're trying to figure out. What do we need to do over here in the time domain so that when we do this thing in the time domain, we end up with, here, what do we need to do so that when we do something in the time domain, we end up with a band of frequencies off to the side in the frequency domain. So that's what this is. This is some kind of signal that comes out of the transmitter that goes into the RF coil that corresponds to a narrow band of frequencies. And so if we use the Fourier transform approach, we could say that what we need is basically, the Fourier transform of some function, like a rect function. And what's that? That's just sort of, minus I, 2 pi, frequency times time for every time. So here we're sort of summing across time. So that's just a Fourier transform. And so the idea is, what is this thing? This is your, whatever frequency selective function. For example, rect. And then this is just our regular Fourier transform. So if we just Fourier transform that, then we should be able to figure out what that is. And so if you Fourier transform that, the answer is of what we need to do in time in order to get a narrow band of frequencies is the following. So that will basically correspond to the flip angle. So how long we leave, or how strong we turn the neurotransmitter, how strong we turn the transmitter on. And then this will be multiplied by the frequency width, and that will be multiplied by a sinc function, which we sort of expected, pi times the frequency width is in there again, times time. And then it will be multiplied by one frequency, minus I, 2 pi, frequency center times time. So this is the answer. So what we're going to do after this is try to figure out why does it make sense that this should be the answer. So what are all these things? So this is just the amplitude of the RF pulse. It controls flip angle. This guy is the width. And notice that appears again here inside the sinc as the argument to the sinc. And then this guy is a sinc envelope. So something that's sort of shaped like this. Sync envelope. And then this is a complex number. So complex amplitude 1, amp equals 1. So that's basically sines and cosines, or alternatively, you could just think of it as a rotating vector of length 1 at one frequency, which is the center frequency. I use those F's here. Let's make them into a regular F. So this guy was the frequency width, and it's also in here. And this guy is the frequency center. So it's kind of a little bit like when we were talking about the FID. Like when the FID starts to decay, what's causing it to decay, the T2 part, it's all these different frequencies building up because of all the different little jostling. So all the guys get sort of jostled into slightly different frequencies. And so there's billions of frequencies, but the way when we end up with the equation, we just ended up with one frequency because we had a special Lorentzian distribution. And so they somehow sort of canceled out and all added up to just one frequency. And the same thing is here. So the same thing is here. It's so how do we make a band of frequencies? We actually just take one frequency and multiply it by this envelope in time. And that actually corresponds to a band of frequencies. And it's worthwhile just sort of stopping for a second to say what does the transmitter do? Like we have, if you go in the back room in the MRI, there's a cabinet, and it's got one of the pieces in the cabinet is the RF transmitter. And what it does is it just makes a 123 megahertz signal, but it actually just makes one frequency. It just makes one frequency very accurately. And so how do you program it? Like if you're writing a pulse sequence, you basically just tell it what frequency, when, so like at what point should you make this frequency, what frequency should you make, you can adjust the frequency, and then you can also adjust the phase of the frequency. So you can say like, should the frequency go up, starting at point 0, should it be like a sine or should it be like a cosine, where along that 0 to 360 should you put the peaks of the frequency. But it just generates a single frequency. And it turns out that's all you need. And then all you got to do is like modulate it like this, and you get a band of frequencies. So before we go to convolution, so that was our gradient for slice select, but then we need a frequency selective pulse, and this is basically what we need to do to get a frequency selective pulse. So everybody got that? So two things required. You have to have the gradient on in order to change the precession frequency at different points in X. And then you got to put a band of frequencies so that you just nail one of those X positions, or a range of X positions, because you just don't want to excite an infinitely thin slice. You want to excite a slice with some thickness. So this is the slice thickness. Okay, so all clear. That part should be pretty clear. So now, how do we get this? So we had to sort of integrate this, and you could sort of integrate it, various ways of integrating it, but let's do something else. Talk about convolution. And so we need convolution for other things. So convolution is very important when we talk about like analyzing MRI data, because if you do something like, say, flash a light, what are we recording with functional MRI? Typically, we're recording this blood oxygenation response. But that blood oxygenation response takes a second or 3 seconds, 4 seconds to come out. And so even if you just do a very short flash, like 100th of a second flash, you'll get something, you do like a very short flash, you'll get, a blood flow response that will sort of look like that. Take a couple seconds to come out. And so to describe that, to go from that to that, that's a convolution. Because this, we call that the hemodynamic response. So that's the hemodynamic response. So in order to sort of make a model of what's going on, or to sort of invert that model to sort of figure out, like, we got this, so what was that? Or we measured this, and this was our stimulus, and so where do we think, the activation in the brain was? So we need convolution for that also. So let's talk about convolution. So convolution it's basically just another correlation. Everything's correlation. So we write out the convolution equation and then just geometrically sort of say what it is. So here's we'll do it in x. So here's a function at x that is the convolution. So this is the convolution. So there's different ways, and it's like the Fourier transform, very similar to the Fourier transform in that it's a relationship between two functions. So in the Fourier transform, you had some signal, and then you had the sines and cosines business. So there was two functions, and you were correlating them basically by multiplying them by each other over all time or over all space. So convolution is the same way, but we'll have two functions like this, function of x, and then there's different ways of writing the convolution operation. So sometimes people just write it as a star, but that could sort of be misinterpreted as a multiply. So sometimes they write it as a star with a circle around it. So if we have another function that we're convolving, so here's another function of x that we're convolving. So what is the equation that defines the convolution between, so this guy means convolution. So what is the equation? So the equation is, it's a very simple equation. It's just sum across all z. Okay, so where did z come from? So z is just another variable that is sort of going, you can think of it as going in the same direction as x. But it's just, we need a second variable because we're going to sort of vary something at z, but we also need x in there too. So it's just another variable. And so what is the convolution? The convolution is just the sum over all z of the one function value at point z times just regular multiply times the other function at a point x minus z. And then we'll just say what this is, and then summed across all z. So basically for one x, get that out of there. So for one x, so here's that x over there. Here it is in those two functions. So for one x, we have to sum across all z. So here's what we're summing across. So z is over there, and over there. So it's kind of like the Fourier transform in that you're going over the entire extent of both of these functions. That's like in the Fourier transform. So the Fourier transform, you have like, say, a signal, and you take the entire extent of that signal, and then you correlate it with this other, with the second function, like this one right here, and this function here is also extended across all t in this case, and then you do something between them, which is basically a multiplication. The only difference is you got this sort of minus thing going on here. So what is that? So let's just draw out the convolution. And one simple way of thinking about the convolution, sort of concrete real world example, is something like a Photoshop filter. So say you've got an image of a face, and maybe there's like a little imperfections or something. You want to smooth it out a little bit. How do you do that? Well, you might apply, like, say, a Gaussian filter to that image. And what does that do? It just goes to each point in the image and kind of mixes some of the neighbors in and sort of blurs the image a little bit. And so that's one way of thinking about what the convolution is. Now, one thing about the convolution is that luckily it commutes, so you can do it either way. So there's several ways of writing it out because of the fact that it commutes. So if you do this is exactly the same thing. So if you take, you could swap G and H in here, and everything would still work. So let's just graphically draw out what this equation it actually means. So if we start off with, and we could call this guy, we can call either one this, but let's just call this guy the kernel. It depends on what textbook you're using. Sometimes they use the other thing, but we'll call that the kernel. A lot of times it might be a small kernel, like a little Gaussian blurring filter. And then we can sort of think of this guy as the image. So like this is like sort of Photoshop. So you've got an image and you want to do something to it, sort of operate on it somehow, magnify the edges or blur up, make it slightly blurrier. So how does that work? So basically what we do is we have some function, which is our image. So say this is our image with like, with the little zit there that we want to get rid of, okay? And so this guy is, call this guy the h of x. That's our image. And then our kernel or our filter, let's say our filter is a little like a Gaussian filter, something like. It doesn't have to be symmetrical, but let's say this is our filter like this. I'll make it a little asymmetrical. So what does the convolution say? So it says go to a position on the filter, the position z. So this is like z going in. Oops. Sometimes I wonder like how my brain works. This is z going in that direction. So let's just take one point. So this is basically g of z. So whatever the value on the y-axis at point z. So that's this. So g of z, we're just doing one. So this guy is a sum, just a real sum, not complex, real sum. So we're just doing one element in the sum. So we take that point, that's g of z, and then we go to the image function at point x. So what we're doing is we're trying to calculate the convolution just for one x. Just for one x. And so the coordinate here is x, and so that the 0 of that x is, could be somewhere else. We'll just put it over here. And so what we're going to do is, for a single x, like this x, so that's the current x that we're considering. We're going to look at whatever that function value is at x, and then minus z. And so here's z. So that's the current value of z. And so then what we're going to do is just go that distance away. So go over to here. So that distance is minus z. And then we're just going to multiply that. So we'll multiply that times that. So, multiply. And then just do that for all z. So what does that mean? It means then we multiply this point times that point, and this point times that point, and this point times that point. So you can see it's convolving, because it's kind of twisting it around like that. So it's like and then we sum up across all z. And so what are we doing, really? You can sort of think of it as a weird it's a weird correlation. Basically, it's just like a correlation, because you're just taking two things and multiplying them by each other and adding them all up. And what happens is, if they look similar to each other, then you'll get a big number. If they're completely sort of randomly different from each other, you'll get 0. If they're similar to each other but sort of opposite, you'll get a negative correlation. So it's kind of like a correlation. And in fact, if you take this sign right here, so if we change that to plus, so if we change that to plus, we get something called cross correlation. So if we change that to plus, and that would be sort of simpler, because then you wouldn't have this flip thing. Then you would just say, then it would be like the Fourier transform, where we just take this value and then multiply by this value, multiply by this value, etc., add up over the whole thing. So that would be cross correlation. And what would that do? That would be like you've got one function and another function, and the question is, if we try them at all different offsets, which one, how much do they correlate at all these different offsets? That's what a cross correlation is. So one thing to keep in mind, I forgot to mention it when we were just going through the equation, this is just one output point, okay? So how do we calculate one output point? We go to a particular x on the image function, and then we take our kernel function, g of z, or filter function, filter, and we paste its 0 at point x. Then we do our multiplication across the whole thing, add up the whole mess, and then we get one output point, in convolution, and we get a single output point. For that x. And then how do you do another x? You just leave that function where it was, just move to another x, and then move this kernel function over, do the same thing. So cross correlation is just exactly the same. So it's just trivially different than convolution. It's just don't do this weird flipping thing. Just leave them unflipped and just see how they correlate with each other. And if we change this guy, so if we make hx equal to gx, then we have autocorrelation. And that's basically just how do you correlate with yourself? And, why would you want to do that? Well, say you have something like this. Sort of looks like a sink. Say you have some function that looks like that. You can see that it sort of correlates with itself with an offset. So if we took this function and we did something like this convolution business, and first we put a copy of the function like here, and then we tried all different offsets. What would you find? You'd find if it was right lined up with itself, or there'd be a big correlation. If you moved it off to the side, the correlation would go down. If you moved it a little bit further off to the side, like something like this, then it would correlate with itself again, because these peaks would be lined up. This peak would be lined up. This peak would be lined up, or sort of. Yeah. So it's a way of sort of seeing does a function correlate with itself? Does it have some kind of internal structure that correlates with itself? So if you can get convolution down, then cross correlation is good too, because you might have two different things that you want to see, are they correlated with each other at different offsets? And so you can see that convolution, remember when I was talking about the Fourier transform, I said, what is the Fourier transform like doing? You just take a function and you correlate it with sine. For a given frequency, you correlate it with a sine and a cosine at that frequency. But I said it was equivalent to taking like a sinusoid and just trying all the different offsets. That's exactly what a convolution is. It's just trying all the different offsets. So you can sort of see it's pretty closely related to it's somehow going to be related to a Fourier transform. Okay, so everybody good on the convolution? So it's another relation between two functions and across, like the whole length of both functions. If your Photoshop filter is very small, meaning it has only, sizable numbers right in around 0, and then it goes off to 0 on the edge, then you can just cut it off, because you're just going to be multiplying by 0, and it won't add anything to your sum here. So you can sort of think of the thing you're convolving it with as a small thing, but the general definition of convolution, it's across all of the length of both of the functions. And, like the Fourier transform, you can extend it to 2D, because like in Photoshop filter is a 2D convolution, because you've got, there's two image dimensions. Okay, so everybody okay in convolution? So it's we'll see that this flipping thing, there's actually sort of, the flipping thing comes in handy when we end up talking about like, hemodynamic response functions. So last but not least, I'll leave the convolution up there. So now let's just talk about the convolution theorem. So how is convolution related to the Fourier transform? So it's very closely related, and we can describe how it's related simply in words. It's actually simpler than the equations, but we'll write out the equations first. And so this is, I'm not sure why they call it the convolution theorem, because it's kind of like a true thing, but that's you'll often see it just called the convolution theorem. And so what is this? This is capital letter for the Fourier transform. So if we take the Fourier transform of two functions, I'll just put them as in time for now. multiplied by each other, it equals the Fourier transform of the two functions convolved with each other. So at this point you're thinking like, how is this going to help me? But let's just write out what it is. So this thing means ft because it's capital. So that means multiply these two things times each other and then take the Fourier transform of it. And then this here means, capital G is the Fourier transform of small g, and capital H is the Fourier transform of small h. So what is, because of the way these things commute, it kind of works both ways. And so one way of just writing it out in words is multiply in one domain, could either be frequency or time, one domain, either, I'll just stick to words. So in one or other domain, well, just one domain, time or freak equals convolve in other. So how does that help us? So let's just try to figure out. So sometimes it's easier to convolve in one domain, especially if you just have something like an impulse. And in other cases, it's easier to just multiply. So let's have our two domains here. So here's the the time domain, and here's the frequency domain, temporal frequency, temporal freak. So when we started off, what we said was we've got the problem is we want a narrow band but off to the side. So we know already that if we have a narrow band of frequencies, so that was our frequency width, and then that's 0. We know that we could Fourier transform that, inverse Fourier transform that into a sinc. So here's a sinc function. Let me make it a little bigger. So we could so we know that one already, because that's one of our Fourier transform pairs. Okay, but what is the problem? The problem is we want this band off to the side. And so how do we get it off to the side? So if we have something that we're convolving with that is just a spike, like that, or two spikes, as the case may be. So what happens when we convolve something with a spike? So this operation here is convolve. So if you convolve something with a spike, think about it. Your convolution is pretty much like a correlation, and since this is all 0, the effect of convolving something with a spike is basically just to make a copy of it. So that's an example of an easy convolution. So if we if we convolve that spike with that thing, all it does is just make a copy of it. You can just think of working it out. Basically, you put this one at all different offsets, and it's all completely zero, and then as soon as you hit the spike, you get something, and for the whole width of the spike, you get something, and then it goes away again. And so what that will do is exactly what we want to do, is it will make a copy of that little band of frequencies off to the side. And it'll make another copy over here, right where that spike is. So that was convolve our central frequency band with two spikes off to the side, and that equals exactly what we want. So something that has a particular frequency width, so that's the frequency width, and it's at a center frequency center. That's not zero, so because here's zero. So now we can look at those spikes and say, oh, but we know what those spikes are. Because if you take two spikes off to the side and Fourier transform that, you get a cosine. So that's one of the Fourier transform pairs. Sinc turns into a little rectangle, spikes turn into a cosine. So what does that correspond to? It corresponds to a cosine. So it would be, so just go up and down like that. What frequency you get depends on where the spikes are. If you pull the spikes in closer, you get a lower frequency. But now we know that since this is going back and forth, between ft f minus 1, so that's Fourier transform and inverse Fourier transform. Fourier transform, inverse Fourier transform. Now we know we're in the other domain, and so since if we've convolved in one and we multiply in the other, so now we just get to multiply, and so multiply is easier. So if we multiply this guy, then this equals our answer. And so what is our answer? Well, our answer is exactly that equation we had before. So here's the 0. And so there's going to be a sinc envelope. So here's that sinc envelope. But it's an envelope, so here's the other sort of piece of the envelope so that I can draw it accurately. And then what's going on inside the envelope? Well, we're just multiplying that envelope times a cosine. So if the cosine happens to be negative, we'll get a negative number. That's why I drew that negative number. And so it's going to look like a cosine, so it'll be like 0 right at the middle. And then it's just going to go up and down, within that envelope like this. And then it'll go to 0, and then it'll come up again, go to 0, come up again. And, same way on the other side. So it's go like that. But what's actually in it? Just one freak. So this is just, just frequency center. That's what the transmitter is doing. So what does the transmitter do? So we have the amplitude of the transmitter because we can turn it up or down. And then we have, the frequency center of the transmitter, and then we got the phase. So we can sort of offset by half a cycle or a quarter cycle here. But amazingly, that's what we need to do. So if you just take a single frequency and just go like woo, 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 woo in time. That's in time. So remember, this is time going this way. So if we just do that with a single frequency, amazingly, we get a band of frequencies, just what we wanted. So it's just like math is strange. So you just take a single frequency and then modulate the amplitude of it like that. And the end result is very counterintuitive. The end result is a uniform little rectangular band of frequencies, which is just what the doctor ordered in order to stimulate a slice. So we could have done sort of in the spirit of like trying to attach all different kinds of things together in math. So we could have just done the Fourier integral and tried to figure it out that way. But this way is kind of more intuitive in a way. So basically sometimes it's easier to convolve something, and then other times it's easier to multiply something. And so basically here's our sinc function, which will Fourier transform into a little band of frequencies. Here's two spikes because we want to move those bands off to the side, which kind of moves the bands off to the side. But then the spikes actually just correspond to a cosine. And then since we're now in the other domain, we can multiply instead of convolve, and then this is what we get. So this is what the transmitter does. So you can control the amplitude very accurately over time of the transmitter. So that makes these little sort of envelope of transmitter strength, but it's only transmitting one frequency. But when you put that together with this sort of varying amplitude, it ends up being a bunch of different frequencies. Okay, so I don't know if that was helpful. At first, when you look at it, you say, like, I had trouble enough with the Fourier transform, and now you got this mess. But it's a way of sort of thinking graphically about these things. You know, it's kind of like a simple way of reasoning about these things. And we'll talk about this again when we talk about one of the things you do in MRI is you can undersample by not collecting all the data. And to really understand how that works, how can you sort of still get an image after leaving out some of the data, we have to do the convolution theorem again. That helps sort of understand why it's possible to undersample and still have enough information to collect the data. So we will use it again. Okay, so any questions about slice select, so we turn on a gradient, and then we play out this frequency selective pulse, which looks like this, and which we figured out by sort of doing our convolution and Fourier transform. And then what we get is just spins that are just excited in a plane so that we can sort of select a slice. Now, we don't always have to select a slice. Sometimes we select the whole head if we're doing a 3D scan. But a lot of times for functional MRI, we're quickly selecting a bunch of different slices. Okay. Slice selection question. So this is how slice selection actually works. I definitely had the gradient idea, but I didn't have the frequency selective idea, and for good reason, because there's more mess involved. But now hopefully it's a clear mess. Yeah. Any questions about the convolution theorem? So the Fourier transform of two things multiplied equals the Fourier transform of one convolved with the Fourier transform of the other, but this is an easier way to think of it. Multiply in one domain, either time or frequency, equals convolve in the other. Okay, any final questions? Oh, good, sort of. The usual stunned silence. First time through, I had the exact same reaction as you. It's just like, how you're trying to help me? This is not helping me. But after I went over it a bunch of times, it helped me. Especially sort of understanding, like the undersampling. We'll come back to grappa and all these ways of sort of undersampling. How does that actually work? Which is used every single day in the scanner. So it's another sort of wall-to-wall. Virtually every scan uses it. Okay, well, I guess we'll leave it there. Sorry to go over. We'll see you guys on Wednesday.